In this video, we will be discussing about engineering Africa's future, the structure and power of GERD. The Grand Ethiopian Renaissance Dam, GERD, is one of the most ambitious projects ever undertaken in Africa. Located on the Blue Nile, known as a bay in Ethiopia, GERD is not just a dam. It is a symbol of Ethiopia's development aspirations, Africa's growing engineering capability, and the continent's determination to shape its own destiny. The dam is often called Africa's project of the century because of its size, impact, and the hope it brings to millions of people who lack reliable access to electricity. Now the construction of GERD is completed. It is the largest hydroelectric dam in Africa and one of the 10 largest in the world. This video will focus on the engineering and technical aspects of the dam, how it was designed, what it is made of, how it will generate power, and the challenges faced during construction. By the end, you will see that GERD is not only an engineering marvel, but also a lesson in how technical knowledge, natural resources, and national ambition can come together to create a mega project that will shape the future. Now, let us dive into the details. The GERD is built on the Blue Nile River, which contributes about 85% of the water that flows into the Nile River. Engineers carefully selected the site after studying the river's flow, the surrounding topography, and the geology of the region. The Blue Nile Gorge provided a natural foundation for a large dam, while the heavy rainfall of the Ethiopian highlands ensured a steady water supply. The narrow valley of the river also reduced construction costs since less material was required to build across it compared to a wider valley. GERD is a gravity dam, meaning it relies on its own weight to hold back water. Unlike dams made of earth or steel, gravity dams are built mainly of concrete. The GERD wall is 145 meters high, which is taller than a 40-story building, and stretches 1,780 meters in length, almost 2 kilometers across the Blue Nile. Behind this wall, the reservoir can hold 74 billion cubic meters of water, creating a surface area of nearly 1,900 square kilometers. This massive body of water regulates river flow, ensures steady electricity production, reduces flooding downstream in Sudan, and provides water storage during dry seasons. However, filling such a huge reservoir has also been a source of tension with downstream countries like Egypt and Sudan, who fear reduced water availability. At the heart of GERD's purpose is power generation. Hydroelectric power works by using flowing water to turn turbines, which generate electricity. The GERD power plant houses 13 massive turbines that together can generate 5,100 megawatts of electricity. To put this into context, Ethiopia's total demand before GERD was less than 5,000 megawatts, meaning GERD alone can more than double the country's supply. This electricity will power industries, schools, hospitals, and households not only in Ethiopia, but also in neighboring countries, since Ethiopia plans to export electricity to Sudan, Kenya, and Djibouti. To construct such a colossal structure, engineers used special materials and modern techniques. Roller compacted concrete was chosen for its strength, durability, and cost efficiency. Steel was used for reinforcement, turbines, and penstocks, which are the large pipes guiding water to the turbines. Rock and earth were used to build the saddle dam, a smaller supporting structure that helps contain the reservoir. In addition, engineers relied on computer models to simulate water flow, seismic testing to ensure stability, and satellite monitoring to oversee progress. The project faced several engineering challenges. Its remote location meant that roads and infrastructure had to be built before heavy machinery could be transported to the site. Financing was also a major issue, with an estimated cost of around $5 billion. Ethiopia had to rely heavily on domestic financing, including public bonds and contributions, since many foreign lenders avoided involvement due to political pressure from Egypt. Hydrological challenges were addressed by constructing diversion tunnels that rerouted the Blue Nile temporarily, allowing construction to proceed without being disrupted by seasonal floods. Political disputes with downstream countries created additional delays and risks, but construction moved forward despite these obstacles. Engineers also had to ensure safety and environmental responsibility. GERD was designed with international safety standards, including 2 spillways to release excess water safely, preventing overflow. Geological studies confirm that the site is stable and resistant to earthquakes. Sedimentation, a major concern on the Blue Nile because of its heavy silt load, was addressed by including systems to flush out sediment from the reservoir. On the environmental side, GERD will help regulate water flow and reduce flooding. But it has also caused displacement of local communities and changes in ecosystems, which remain issues of concern. Although primarily an engineering project, GERD also carries geopolitical significance. For Ethiopia, it represents independence and self-reliance, showcasing the nation's determination to use its resources for development. For Africa, GERD is a statement that mega projects can be designed, funded, and executed largely by Africans. For the region, the electricity generated by GERD promotes integration, since countries can share energy resources and strengthen economic ties. GERD has also become a school of engineering for Ethiopia. Thousands of local engineers, technicians, and workers have gained practical experience in managing a mega project. Universities in Ethiopia have incorporated lessons from GERD into their engineering and hydrology courses. The knowledge gained will benefit Ethiopia and Africa in future infrastructure projects. To understand the scale of GERD, it is useful to compare it with other dams. The Aswan High Dam in Egypt, built in the 1960s, has a generating capacity of 2,100 megawatts, about a third of GERD's. The Hoover Dam in the United States generates about 2,000 megawatts, again far smaller than GERD. Although China's Three Gorges Dam, the largest in the world, is much bigger with a capacity of 22,500 megawatts, GERD still ranks among the top 10 dams globally and is the largest in Africa. This places Ethiopia and Africa prominently on the global map of engineering achievements. In summary, the Grand Ethiopian Renaissance Dam is much more than concrete, turbines, and water storage. It is a statement of ambition, skill, and hope. As the largest hydroelectric dam in Africa, GERD stands as a testament to Ethiopia's determination to use its natural resources for development. From an engineering perspective, GERD is a gravity dam built with advanced materials such as roller-compacted concrete. Equipped with 13 massive turbines capable of generating more than 5,000 megawatts of electricity. Its construction faced challenges of geography, financing, and politics, but these were overcome through planning, innovation, and national commitment. GERD shows the power of engineering to transform societies. It provides electricity, creates jobs, develops local expertise, and strengthens regional cooperation. At the same time, it highlights the need to balance technical ambition with environmental and geopolitical realities. Ultimately, GERD is not just a dam. It is a school of engineering, a symbol of African progress, and a foundation for future development. By studying GERD, we learn not only about hydroelectric power, but also about how nations can dream big and engineer their futures. Thank you for watching. Please like, share, and subscribe for more videos.